Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Hope you guys are all doing well. Let's jump into it. Okay, so let's do a quick recap. Let me make sure I can actually see the chat here. Okay, so last time we started talking a little bit more about derivatives. We started looking at the properties and started looking at how to compute them in short order. So we looked at the first derivative test, which helps us identify where maximums, minimums, increasing and decreasing may occur. And so we know that we can find the critical points. These are the points where the derivative is 0 or undefined. You plot those on a number line, you pick random numbers in between them, and you test for the sign of the first derivative. Whenever the first derivative gives you a positive sign, that means you're increasing. When it gives you a negative sign, that means you're decreasing. If you happen to increase and then decrease, and you pass through a point where the function is continuous, it means you hit a maximum. If you happen to decrease and increase, and you pass through a point where the function is continuous, it means you are a minimum, right? Otherwise, you don't really, you can't really conclude max or min from this test, but you can generally conclude where you're increasing and decreasing. We also looked at the concavity test. This is a test that tells you about inflections, concave up and concave down, which is important in its own right. It uses the second derivative, and you do pretty much the same thing. Find where the second derivative is equal to 0 or undefined. You plot those points on a number line, you test them in the second derivative. In this case, the positive, when the second derivative is positive, it means that it's concave up like a cup, shaped like a smiley face, positive, feeling happy. Or if it's negative, it's down like a frown, feeling negative, feeling sad. And if you switch from concave up to concave down, or from concave down to concave up, you go through what's called an inflection point if you're continuous at the point in between those two. And yeah, we also summarized a lot of the different functions that we were looking at. These are the important functions for us, or the important, I don't know what you want to call them, computations, categories, whatever. So there's the original function, which we're very used to dealing with by now, talks about position, current state, location, things of that sort. The first derivative tells us increasing, decreasing, maximums, minimums. It also tells us about things like, rate of change. How fast are we moving? How fast is the output coordinate moving in relation to the input coordinate? You can determine all that behavior from the first derivative test. We have the second derivative, which can tell us about concavity and inflections, and the concavity test will tell us how to do that. We also spoke about the existence of a derivative. It was easier to say where it does not exist. Where a function is not continuous, it does not exist. If there's a sharp corner, it does not exist. And if there's a point where your function essentially would have a vertical tangent line, won't exist there either. But then we moved on to the fun stuff, right? So that was all the conceptual stuff. It's going to be important later, but it was just basically an information dump over the past 2 classes. Now we're actually getting to the fun stuff, properties of derivatives, doing calculations with them. We learned that we can factor constants in and out of derivatives. We learned that derivatives distribute across sums. They do not distribute across products and divisions, so don't do that. We also learned a couple more rules, which we didn't prove, but I just gave them to you. The derivative of a to the x is a to the x ln a. This is our exponential function. You might recognize that form, where the base is a positive constant. In particular, derivative of e to the x is e to the x, and this is actually a very special thing. It's the only the only fundamental function, other than the 0 function, that is its own derivative, and that's actually saying a lot. We have the chain rule. Now, this is actually a super important thing. You do need to know the chain rule. You need to know everything that I put in boxes here. But the idea is you need to know how to differentiate a composite function. When you have a function inside of another function, something complicated that looks like that, the square root of 1 minus x squared or something like that. You differentiate the outer function based on derivative rules and then you multiply by the derivative of the inner function. That was the chain rule. Then I sort of left you with a few examples here, which technically we don't know all the rules that apply yet. But we we'll know enough. So let me just, so now let's actually begin. So we have to try these guys. But first, what do I want to say? Note, the chain rule allows us to generalize basic formulas, right? Remember, the chain rule basically tells you when you have an inside function, it tells you how to deal with that is by you differentiating the outside and then you multiply by derivative of the inside. So, for example, if I ask you what if I wanted to differentiate e to not just x, but like some function of x, like g of x or something like that. How do you actually go about doing that? Well, what you can do is you can think of this g as an inside function, right? So the e to the x is your outer function, and then I took something and I plugged it into that function. And so this tells us how the chain rule tells us how we can deal with this, right? So the derivative of e to some function plugged in by chain rule. Well, you differentiate the outer function, but what do you do to differentiate the exponential? Well, the e to the x, you do nothing. You get back the original guy. But then the chain rule says now you need to multiply by the derivative of the inside function. So you have to multiply by g prime of x. And so the chain rule tells us that we can generalize the rule of differentiating e to the x to differentiate e to the anything. In fact, this kind of leads to a rule that I rather memorize in this form. E to the u is u prime e to the u. Someone's trying to get in here. Okay. So this is like the chain rule version. This is the chain rule version of that rule. Okay. Now, so maybe I'll do some examples. For example, if I ask, what is the derivative of e to the square root of x? Well, that's just going to be 1 over 2 rad x, e to the square root of x. Or you just differentiate the derivative of the power times the original function. That's how you differentiate an exponential. The derivative of e to the 1 plus 1 over x. Let's make it a little nicer. Let's do x plus 1 over x. That is going to be the derivative of the power times the original function. Right? So the chain rule gets us to, allows us to differentiate something that's like way more complicated and with ease pretty much as well. We can also generalize this guy. Remember when we had the derivative of a to the x is a to the x ln a. According to the chain rule, if I had an inside function, it was a with some function plugged inside. Then we're going to multiply by derivative of the inside and then take the original, multiply by ln a. And that's, this is the chain rule version. So, example there. We already saw how to differentiate 2 to the x. What if I had 2 to the x squared? Well, that's just going to be 2x times 2 to the x times ln of 2. Just plug it into this formula. Differentiate the power, x squared. Differentiate the power, rewrite the original function, multiply by ln of the base, right? That's what this rule tells us. right? So yeah, that's nice. So the chain rule is pretty cool. We're actually going to use the chain rule to derive some simpler things. We didn't derive the chain rule itself. That one is kind of sophisticated. Not totally crazy, but I don't want to spend the time on it in this class. But we're going to actually use the chain rule to actually figure out some other rules. What else do I want to say? Well, if you only want to memorize minimum, it is better to memorize the chain rule versions of any given rule. And why? Because you're getting your more bang for your buck. They include the basic versions. And this is true because the derivative of x is 1. So, for example, if I memorize this, then that means what is my derivative of e to the x? Well, it's going to be the derivative of x, right? That's going to be the u prime times the original function, e to the u. But the derivative of x is just, well, 1. So that just gives you back e to the x, right? So you get the rule back. Right? So the basic rules are just like the chain rules, except your u prime is 1, right? So if you want to memorize one thing, if for some reason you have trouble memorizing a lot of the formulas, you can memorize like half the formulas I'm going to give you, because just memorize the chain rule version, you automatically memorize the basic version. Although some like the derivative of e to the x equals e to the x is going to be something that you're going to use so often, it's like you're going to remember anyway without even trying. But if you want to focus somewhere, I would say focus on the chain rule versions. What else do I want to say? Nothing right now. Let's look at these guys. Oops. It's funny. Because I did make an oops. Okay, so here is an example that I want to do 2 ways. So 1. So you can first expand and differentiate. So you can say the derivative of the square root of x plus 1 over x squared. We know how to expand a square. You square the first term, take 2 times the one term times the other term, and then you square the last term. Now it turns out, well, let's. How you would do this is the following. I'm going to tell you the rules for this right now, but at this point, we actually don't know them. So here, what you can do is you can, we know the derivative of that. the derivative of this, it turns out, is going to be minus x to the minus 3 over 2 minus 2x to the minus 3. Did not give you these rules yet. I'm going to give you these later today, like how you would go about actually doing that. And 2, to use the chain rule.
I don't.
So the chain rule can save us from expanding, because now what happens is we have an inside function and an outer function, right? So the outer function is a square, the inside function is the radical x plus 1 over x. And so what we can do is we can differentiate the outer function, which we know how to do. It's the same as differentiating a square. Leaving the inside alone, and then multiplying by the derivative of the inside function, which we now know is 1 over 2 rad x minus 1 over x squared. And if you expand this, you'll realize you'll get that, right? So that's one way you could figure out that those rules actually work. Okay, so you can try that. We had another example. Let's have one more. I just want to get through.
Wait, so quick question.
Yes.
So for that first example, is the answer what you put under when you say use the chain rule? The 2 times,
Yes.
or that's
Yeah,
the answer, right?
Yeah.
Okay.
If you multiply it out to try to check, is it the same as the answer that I had before, then you would see that it is. I just want to show you that there are sometimes multiple ways to skin a cat. We could actually find the derivative of this several ways. However, in this case, I think it would be clear that you actually don't want to use the first method, right? We would not want to use the first method here. Right? You don't want to expand 100 power. You're going to have 101 terms. It's going to take forever. Then you differentiate all those. It's not gonna be fun. So you can use the chain rule. So this is just an example to show you the power of the chain rule. So what we can do is the derivative of square root of x plus 1 over x to the 100 equals, and again, this is something that I haven't told you yet, but I will very shortly. The derivative of x to the 100th power is actually 100 x to the 99th power. And I'm going to show you why in a little bit. Don't worry about it right now. But that's what we do. You differentiate the outer function, leave the inside function intact, then multiply by the derivative of the inner function. And that would be your answer. one I also haven't told you yet, but sorry, that is a square instead. Well, we actually saw a bunch of examples like this. These examples that aren't really worth anything now. I just wanted you guys to try stuff when we weren't in class. But now that I wrote it down, I'm just trying to get through them. You want to multiply the derivative of the power times the original function. Also this one. Multiply by the derivative of the power, which is 0 minus 1 over 2 rad x times the original function times ln of the base. Okay, so once you know the rules, it's actually not going to be a big deal. Let's get some more rules so we can do cooler stuff. But you guys can copy that down if you want. I actually have way more examples for you guys to do. Like, once I tell you all the rules from this section, I have like 19 examples we're going to go through. Like the point is, like, by the time we're done with derivatives, like, you guys are going to be experts. Okay, so that's the plan. Let's move forward. So we know how to differentiate the exponential function. We know how to differentiate select few functions like 1 over x, x squared, any constant, something that looks like a to the x, something that looks like e to the x. What other guy would we want to know? How about the logarithm? Let's figure out the logarithm. What about the derivative of ln of x? Let's do the natural logarithm. So we don't know what that is. So here's a trick we can do. Let's actually derive it. And we're not even going to use the limit definition, even though technically we could. What we're going to do is set y to be the log. Now, the thing is, then what we actually want is y prime. If I can find y prime, I know how to find that. Okay, so now, because I don't know what the logarithm is, what I would do is I would actually rewrite this equation to like get rid of the logarithm. That's going to be the trick we're going to use. So this would become what? If I rewrite this without the logarithm, what does it become? We have like a test in like a week, right? We need to start remembering this stuff. What would that become if you rewrite that without the logarithm?
Wouldn't it be y, hold on, I'm sorry, e to the y power equals x?
Yep, that would be it. We can write it as e to the y power equals x. Now what we can do is we can actually differentiate both sides of this equation. Okay, now how do you differentiate e to the y? Well, notice that that is not x, which means we have a rule for that case, which I gave you up here. The derivative of e to the u is u prime e to the u, where that u can be anything, including y. So the derivative of this by that rule is going to be y prime e to the y, right? And this happens by chain rule. Derivative of the x is 1. We actually knew that, which means my y prime, the guy I want, I can actually solve for it. That's just 1 over e to the y. And now you say, well, what is e to the y? Well, e to the y is x, isn't it? So this gives you that your y prime is 1 over x. Or in other words, the derivative of ln x is 1 over x. Now, of course, your x cannot be 0, but it couldn't be 0 in the first place, right? Because it was inside a logarithm. So that's a rule. Now, of course, you can memorize that rule, but I would rather you memorize this rule, chain rule version. The derivative of ln of anything is going to be differentiate the outer function, which is 1 over the thing, then multiply by the derivative of the inner function, which is u prime. So you get u prime over u. And I'd rather you memorize that version. Because even if your u is x, your u prime becomes 1, you get back the old rule, the basic rule. So that's how we differentiate a logarithm. So a natural logarithm, really the only one we should care about. So example, if I ask you, what is the derivative of ln of 1 plus x squared plus 1 over x? Then you're going to put that thing in the bottom, then put its derivative on top. That's your answer. I mean, you could simplify that by multiplying the top and bottom by x squared, but I'm not going to do it. And yeah, so that's now another rule we know. All right, we're going to learn a bunch of rules. Now, let's talk about another very famous rule, which is beloved by calculus students all over the world. Let's talk about something called the power rule. We wish to know the derivative of x to the n. N is a constant. So sort of something that looks what we would think of as a polynomial, but it's not really, because if your n is a fraction or something else, it's not a polynomial. But x to a power is a very common type of function, a power function. And we want to know how to differentiate these guys. So how we differentiate power functions is called the power rule. It's actually given a very special name because this is a function that is near and dear to our hearts. How do you actually go about doing that, though? So let's look at doing this directly. Can get annoying. Okay, so let's say, example, I ask you, what is the derivative of, say, x cubed? Now, we don't have a rule yet. We have no idea what this could be. Not really. X cubed is like this weird function that does this little thing that has an inflection at the origin. Like, how do you actually go about doing that? You see a function that you don't know how to deal with, and you want to find its derivative, you go back to the definition. The derivative of x cubed is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. So now you have to expand this. Now you have to remember how to expand the cube. So that's going to be x cubed plus 3x squared plus 3x h plus 3xh squared plus h cubed, because remember our Pascal's triangle, over h. This guy would cancel. there'd be a common h left. That guy would cancel. And then you can plug in h equals 0. You'll realize that you're left with 3x squared. And you're like, well, that's neat. Then you start to think, well, we actually looked at x, and the derivative of that became 1. We looked at x squared, the derivative of that became 2x. Now the derivative of x cubed is 3x squared. You might start getting an idea of what the pattern is. We also saw that derivative of x to the 100 was 100x to the 99, even though Jhevon never told you why that was true. But the pattern fits. It's like when you have x to a power, it seems like what you do is you take that power, you put it in front, and then you subtract 1 from the power. If you notice that that's the pattern that's happening here. How do you know that happens in general, though? What about the derivative of x to the 100, right? Won't want to do that. What about something even crazier? What about, you know, the derivative of x to the square root of pi? I don't know how to do that. Like, if I plug in x plus h to the power of radical pi, okay, I don't know where to go here, right? So that's kind of complicated. So let's actually figure it out. Turns out we can do it in a similar way. We can derive the general rule similar to how we did the derivative of ln x. Set y equals x to the n. Of course, we want y prime. Now, clearly, we can get some easy low-hanging fruit here. Of course, if our x equals 0, then this means that your y equals 0, which means that your y prime is 0. Okay, that's cool. So now, if x is not 0, and say x is positive, and again, we want to avoid complex numbers. This means we can actually do something that's really nice. The thing is, dealing with the power is complicated because this nth power either can be very big or it can be something very weird that I don't even know how to expand. And so when we have a power that we don't know how to deal with and we want to actually deal with something and the power is making it complicated, what do we do? What is the standard strategy to deal with annoying powers of stuff or stuff raised to powers?
You want to get rid of the power?
Yeah. How? How do you remove the power, like legitimately, without doing some kind of hocus pocus math? Do we know anything that can get rid of the power? Or get the power out of the power, get it out of the exponent?
Yeah, what did you use, a log?
You can log. That's what logs do, right? So that's, you know, so me asking that question is I'm trying to lead the witness. There are certain things that you should just understand go hand to hand in math, right? So if someone asks you, oh, something is being added to both sides of an equation and you want to isolate the other guy, what do? You subtract, right? You automatically know that subtracting is like the opposite of adding, right? In the same way, you should know a logarithm is the opposite of raising something to a power and vice versa, right? So if you want to undo one, you use the other, right? Same way you'd use division to undo multiplication, you'd use subtraction to undo addition. You should just know I can use logarithms to undo powers, right? So that's what we're going to do. So since I'm assuming that the power is positive, it means I can throw it inside a logarithm. Now, the log rule says I can bring that power down. Now, I'm going to do the same trick, differentiate both sides. How do you differentiate log of ln of something? The derivative of the thing over the thing itself. Right? How do you differentiate n times ln x? Well, n is a constant. So we want to differentiate a constant times ln x. How do you differentiate a constant times a function? Well, you leave the constant alone and you differentiate the function. And we already knew how to differentiate that function. We derived that that was 1 over x. So this means that our y prime is going to be n times 1 over x times y. But what is y? Y was x to the n. So this is going to be n times 1 over x times x to the n. So this is n x to the n over x. Laws of exponents tells you subtract the powers, right? So it's going to be x to the n minus 1, which is the power of x in the bottom, right? So it's n x to the n minus 1. So it turns out that that pattern that we thought is actually how it's done, and we could use logarithms to figure that out. The derivative of x to some power is nx to the n minus 1. This is a very important rule. This is called the power rule. There's one for integrals, but usually when someone says power rule, they're talking about derivatives. So that's the power rule. That's how you differentiate x to a power. So if I said, oh, what is the derivative what is the derivative of x to the 7? Well, it's 7x to the 6, right? Bring the power down, subtract 1 from the power. What is the derivative of x to the 11? Well, it's 11x to the 10, right? What is the derivative of x to the 100? Well, now you see why it's 100x to the 99. It has to be, can't be anything else. What about that weird guy that I randomly put? X to the square root of pi. Well, it's going to be the square root of pi, x to the square root of pi minus 1. It doesn't matter what the constant is, how it looks. That's how you differentiate x to a constant power. This is just how it's done, right? That's the rule. This is why the rule works. So this is called the power rule. Now, I want you to notice something interesting. Interesting fact. We can rederive, is that a word? Rederive a lot of our old formulas. So, for example, we know that the derivative of x is 1. Why is that? The derivative of x, well, that's just the derivative of x to the 1. By the power rule, that's 1 times x to the 0. X to the 0 is just 1. So we have rederived the fact that derivative of x is 1, right? In a lot quicker than we did the first time. We also derived the derivative of x squared. Well, we now know that that is 2x to the 1, or 2x. Right? So that's by power rule. Last time we had to do the limit definition, we had to expand, blah, 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 all sorts of stuff. The derivative of square root of x. We know that that's 1 over 2 radical x. Does that agree with our rule here? Well, yeah, because the square root of x is just x to the 1/2 power. Then I can bring that 1/2 power down and then take 1/2 minus 1. This is 1/2 x to the minus 1/2, which is, of course, 1 over 2 rad x. What if we wanted to find the derivative of 1 over x? We could do that too. We derived it last time by the limit definition where I had to multiply and divide by the LCD and went through a whole bunch of stuff. But here, just realize that you could write that as x to the minus 1 power. Then you bring that minus 1 down, subtract 1 from the power, you get minus x to the minus 2, which is minus 1 over x squared. What about the derivative of a constant? It turns out you could actually derive that from the power rule. Power rule is very versatile, right? So derivative of a constant. Well, a number is the same as that number times 1. 1 is the same as x to the 0. The derivative property tells me that I can factor that constant out. X to the 0 tells me, well, the 0 comes down, I subtract 1 from the power, but that's just 0. So I can derive that the derivative of a constant is 0 from this rule. Right, so there are tons of things you can do. So there are a lot of things that we painstakingly derived before that they're actually all pretty easy to get from the power rule. Very important rule. You should know it. It's also how, by the way, to have a little throwback here, how I figured out these guys, how I figured out these guys right here, right? So when I had the 2 over radical x, I wrote it as 2x to the minus 1/2, bring the minus 1/2 down, subtract 1 from the power, minus 1/2 minus 1 is like minus 1 over 2 minus 2 over 2 gives you minus 3 over 2. And so, yeah, those were the derivatives right there. So yeah, all that's really nice. So that's the power rule. So it's another rule we know now. And by memorizing that rule, you can essentially forget the rules of all the things that I derived, like the first day I gave you the limit definition of derivative, because all of those functions that I told you about, you could actually just figure it out by the power rule. So yeah, you can memorize this one rule, and then you don't have to memorize all those other rules. Just in case you hate memorizing stuff, like if you're someone like me. I also had an example, another example here. Don't forget our properties. So, for example, what if I ask you to differentiate (3x to the 7 minus 4 over x plus 5 over the cube root of x? Looks complicated. By the way, the conjugate of a cube root isn't just a matter of like changing the middle sign or something like that. It's like actually more complicated. You need like 3 terms with these weird powers. Well, they're not weird if you remember the sum and difference of cubes formula, but most people just wouldn't remember how to do that. So these would be very annoying to figure out with the limit definition is the point. However, with the power rule and with the properties of knowing that I can differentiate a sum by taking the sum of the derivatives, and if there's a constant in front, I can just leave it and just differentiate the function part, I can immediately just realize that, let me write out like one step that you don't have to write out, but just to make sure I'm not losing anyone. You leave the 3 alone, the power rule tells you how to differentiate the x to the 7. 7x to the 6 minus you leave the 4 alone, and the power, oh, maybe I should actually do that. I probably would write this out, by the way, just to make sure. Of course, for the power rule to work, you want to write things as powers. If I wanted to write 1 over the cube root of x as a power, how would I do it?
Is it x to the negative 1/3?
X to the negative 1/3. Right. So now, this line you wouldn't have to write, but you can if you want to. You just realize, well, I'm going to just leave the constants out front and differentiate the function parts with the power rule. So that becomes 7x to the 6. The 4 stays. This becomes minus 1x to the minus 2. The 5 stays. This becomes minus 1/3 x to the minus 4/3. Right? Subtracting 1 from the power. You can always think of 1 as something divided by itself. You can always think of 1 as, I accidentally clicked off the screen just now. You can always think of 1 as something divided by itself. So if you have minus 1/3 minus 1 is the same as minus 1 minus 1 over 3 minus 3 over 3. You get minus 4 over 3. But many of you can probably actually skip to this. The 7 times 3 is going to become 21. This will become a plus 4x to the minus 2. This becomes minus 5 over 3 x to the minus 4 over 3. And that's how you do that. So yeah, we've come a long way. Now, in very quick order, we went from barely being able to differentiate something like x squared to now we can differentiate all sorts of interesting things. And we got this far very quickly because of the chain rule. So it's very nice that we didn't have to go through the limit definition to figure out any of this stuff. The chain rule is a very powerful ally. In fact, I'm going to derive 2 more rules for you guys, and I'm going to use the chain rule to derive the second one. So that's going to be nice. Now, let us deal with differentiating products and what's sometimes called quotients, divisions. So I mentioned the derivative of a sum is the sum of the derivative. Derivatives distribute across sums. It turns out this does not work for multiplication. So again, note d dx does not distribute across multiplication, division. How can we see this? You can see this with an example. So here's the thing. We know the derivative of x squared is 2x. But x squared is the same thing as x times x, right? So let's say I wanted to differentiate x times x. Would I get the right answer if I distributed? Well, if I take the derivative of x and then I multiply that by the derivative of x, well, that would just give me 1 times 1. That would give me the answer 1, which I know is the wrong answer. I know how to differentiate x squared now, like at least 2 ways, right? Right? So, and obviously if it doesn't work for multiplication, it's not going to work for division because multiplication and division are very well linked. But you could do a division if you wanted. So let's say you looked at x squared. Now what you want to do is you want to think of this as x cubed over x. Now, if we distribute the derivative, that would be the derivative of the top divided by the derivative of the bottom. That would give you 3x squared over 1. That would give you 3x squared. Again, wrong answer. So the derivative does not distribute. Right? If I put myself in a situation where I know what answer I should be getting, and I try to do that kind of thing, it doesn't work. Okay. So now the question is, how would we actually do it? If I have one function multiplied by another, if I have f of x times a g of x, how do I differentiate such a thing? Well, let's go back to the definition. Right? Because here, these functions are way too general for me to do any little trick with them. Like, it's not like a logarithm where I'm like, oh, let's raise to an exponential or something like that. Like, I don't know what these functions are. They could be anything. So we have to go back to the definition. Let's see what we can get from the definition. The derivative of f of x times g of x is, well, the limit as h approaches 0 of, we're going to plug in x plus h, minus plugging in x all over h. Now, here's a little sometimes, like pulling, and subtract something convenient to be able to, and to be able to rewrite things in a nice way. So it turns out you can do that here. And so what I'm going to do here is h f of x is something. So I'm essentially adding 0. It's not going to do anything. But now what I'm going to do is I'm going to split the fraction. F of x plus h g.
Professor, I can't hear you. I can't really hear you. I don't like you keep cutting like in and out.
Hello, can you hear me now?
Yeah, I can hear you now.
Okay. All right. I'm just talking what I'm doing anyway. So you can get that. Now, here's what I'm going to do. I'm going to actually factor off this here. The g of x plus h is a common term. I can factor that off. You'll also notice that the f of x plus h is a common term in the second one, and I can factor that one off also. So what I'm going to do is I'm going to take this one. And then factor off the g of x plus h. Plus, now I can factor off the f of x. And here I have g of x plus h minus g of x all over h. Now, limits distribute across sums and products. So this guy can distribute across everybody. So here I'm going to have the limit as h approaches 0 of f of x plus h minus f of x over h. That's just like a sentence we've heard so often now, like we know what that is automatically. Times the limit as h approaches 0 of g of x plus h plus the limit as h approaches 0 of f of x times the limit as h approaches 0 of g of x plus h minus g of x all over h. Now that guy is what? Well, that's the derivative of f, isn't it? What is this guy? Well, as h approaches 0, g of x plus h goes to g of x because I just plug in h equals 0. Plus, well, there's no h in the f of x, so that just stays. It's essentially a constant compared to the limit. And this one, again, is by definition the derivative of g. And so that is actually how we differentiate a product. So this means that the derivative of f of x times g of x is equal to f prime times g plus f times g prime. This guy is called the product rule. Super important rule. It tells us how to differentiate products. In fact, let's test. Differentiate x squared in a very complicated way of thinking of it like this x times x. Does this rule still give us the right answer? Well, if I pretend that this is f and that is g, then you would get that f prime equals 1 and your g prime equals 1. And so this would be the derivative of f times g plus f times the derivative of g. This is f prime g, and this is f g prime. And hey, you get 2x. Which is the right answer, right? Now, of course, you would never actually differentiate x squared like this, but it's good to know that it's actually consistent with something that we already know to be true. So that's how you differentiate products. It's called the product rule. Super important, muy importante. Okay, moving on. What about divisions? Now it turns out because we went through all this trouble for the product rule, division is actually going to be a lot easier, because the thing is, I can rewrite a division as a product. Right, just think of it as g of x to the -1 power. And then I can do the product rule. Product rule says differentiate the first function, leave the second function alone, plus leave the first function alone, and differentiate the second function. Now, what is the second function's derivative? Well, you can think of the g of x as an inside function. The -1 power is an outside function. We can use the power rule to differentiate that. The -1 comes down, leave the inside intact, subtract 1 from the power. What I applied here was the chain rule. And so what we have then is f prime times g to the -1 minus f times g to the -2. This is the same as f prime over g minus f over g squared. I can create a common denominator. Sorry, missing times g prime. Ran out of screen space. So now we get f prime g minus fg prime over g squared. This is called the quotient rule. The derivative of f divided by g is f prime g minus f times g prime over g squared. Some students know this as like low d high minus high d low over low c. I don't really care what mnemonic you come up with to remember this. I've always just remembered it as the formula. Like I literally just say that whole thing in my head, like f prime g minus fg prime over g squared. Some people have all sorts of things that they come up with to remember this. But however you do it, make sure you remember it. But that's called the quotient rule.
Wait, how did you get the G prime? Would you be able to scroll up for a second? I think I might have missed it.
Oh, it's from the chain rule part.
Okay, wait, I see it now. Okay.
So remember, it was the g of x to the -1. You differentiate the outer function, then multiply it with the inside function. So, I mean, it's pretty obvious, but product rule differentiates products. Quotient rule differentiates divisions. Chain rule differentiates composite functions. So based on what you're looking at, you know what rule you want to pick. Now, the chain rule pretty much always applies. You can literally always use the chain rule every single time. However, the product and the quotient rules are different in the sense that it can be overkill to use them. So it's not like every situation where you see a product, you use the product rule. For example, if you have a product where one of the functions is a constant, then just use the constant factor rule. You wouldn't use the product rule. That's like overkill, right? You could use the product rule and you should still get the right answer, but students often don't, because while they're trying to use the product rule on something that they shouldn't be using the product rule on, they tend to forget all these other little rules, like the derivative of a constant is 0. That happens a lot. When you're a new student, you're just learning something, it's going to be hard it's going to be harder than you realize. You're going to think you're going to be able to do it, but I'm just giving you a heads up. It's going to be harder than you realize to actually keep several of these new notions in your head at a time. So don't kind of put yourself in a position where you have to like have multiple rules in your active working memory at the same time while you're solving a problem. So there are times when it's like, you don't want to have to remember the product rule and remember that the derivative of constant is 0 and remember you'll get in trouble eventually, right? So I'd rather in a situation like that, just don't use the product rule, use the constant factor rule. You tend to want to use the simplest rule you can get away with, and you're going to want to actually look for that. And we're going to get a lot more practice with that coming up. But let's look at some examples, the examples I want you guys to do. And you, at this point, you know everything that you need to know to do them. So let me just write them out. Examples. Mucho examples. Okay. Find y prime. By that I mean the derivative with respect to x of, that should be 4. Now, we're obviously not going to get through all of these now, but it's very important that you actually try them before next class, because we're going to go through them rapid fire next class, and it's going to be important for the quiz and the test coming up. So I believe you have a quiz on Sunday and your test is on like Thursday or something like that. Yeah. 1, y equals x cubed e to the x. 2, y equals the square root of x, e to the x. 3, y equals 3x squared ln x. 4, y equals x times the square root of x. 5, y equals x plus 1 over x plus 2. 6, y equals x cubed was actually x squared over 3. 7, y equals 3 over the square root of x. 8, y equals 4 over x cubed. 9, y equals ln x over e to the x. 10, y equals e to the x times ln x. 11, y equals x cubed plus 1 to the 20th power. 12, y equals e to the x cubed plus 1. 13, y equals ln of x cubed plus 2x plus 1. 14, y equals the square root of 2 minus x to the 4th. 15, y equals x plus 1 over x plus 4 to the 6th. 16, y equals x over e to the x cubed. 17, y equals 2x plus 1 to the 8, x cubed plus 1 to the 5th, 18. Y equals similar to that guy, but a division instead. 2x plus 1 to the 8 divided by x cubed plus 1 to the 5th. And 19, y equals similar to that one, but now I throw in an ln. Which looks like I made it more complicated, but if you remember about your logs, 19 is actually a lot easier than 18, believe it or not. So those are the guys. I would suggest you practice those. And let me just check something here. Yeah, so we're gonna stop there. I mean, I'm leaving it up for you guys to like take a screenshot or whatever. But in the meantime, let me make sure to look this up. Yeah, so your first test is on March 18th. That's during regular class time. And your next quiz is March 14th. Right, so that's like 3 days from now. And that covers up through topics 13. Well, no. The quiz will cover up to 12. I'll put 13 as a bonus. So let me just amend that. Let me put that in here as well. So next quiz, quiz 3. March 14th, topics 9 through 12. Topic 13 is bonus. So you need to make sure, and then test 1, this is March 18 during class. And it's topics 1 through. So let's see here. I mean, we could rush and start topic 13 on Monday, but then to rush through that on Monday and then give you a test on Thursday, it's probably not nice. So even though on the syllabus it says the test that goes up to 13, it's topic, I'll do it also 1 through 12. With topic 13, learn that for a bonus. So I might actually bonus problems on 13. That way we won't have to rush. We can just make sure we finish topic 12. We understand everything about that, but that will cover everything. So which means the homework that is due is everything up to section 3.4. So all homework up to 3.4 is due next week. I believe it's a day or two before the test. So it's probably like Wednesday at midnight or the Tuesday at midnight. I forget, but it needs to get done by next week. Hopefully you've been keeping up with the homeworks and you don't have to like cram through everything. You only have to do the topics that we just did. But yeah. So that's it. Unless there are any questions, we're gonna go. So I don't know. Hopefully that's cool. Okay. All right. Thank you for your time and attention. Hopefully you have a good day and have a good weekend, and I will see you guys in the next one. Ciao.